do share screen. Okay. So welcome everybody. We are proceeding in the topic, which is Dirac equation. So a quick recap. Is everybody with me?
Yes.
What did we do? So we find out, where were we? Okay, so Dirac was looking for an equation that replaces the Klein-Gordon equation and has first order derivatives both in space and time, right? So I dt psi equal minus I alpha j I. With alpha j and beta j, we show that they must satisfy, in order for this equation to be compatible with Einstein's relation, namely it has to satisfy Klein-Gordon equation as well. Then the alpha and beta matrices are they're not simply numbers, they are matrices, and they obey certain rules. Right, alpha x squared is alpha y squared is alpha z squared is I. Alpha j alpha k plus alpha k alpha j is equal to 0 if j is not k, and alpha j beta plus beta alpha j is equal to 0. I is a unit matrix. Now we show that this alpha and beta has several properties. They are traceless. Their eigenvalue is lambda plus minus 1. Lambda is plus minus 1. Have an even dimension. And 4, we said that they are Hermitian. Since there are only 3 such matrices in 2 dimensions, these are the polymatrices, right? Sigma x 0, 1, 1, 0, sigma y is 0 minus I 0, sigma z is 1, 0, 0 minus 1. And Dirac was forced to conclude that these alphas alphas and beta have to be a 4x4 matrices, or the representation needs to be a 4x4, which means that the wave function psi that solves this equation has to have 4 components, and so it's known as the Dirac Spinor. So psi is psi 1, psi 2, psi 3, psi 4, and the wave function that solves Dirac equation is known as the Dirac Spinor. And in these 4 dimensions, the alpha and beta matrices can have several representations. The most notable one is the Dirac poly representation. Where beta is I 0, 0 minus I, and alpha I is 0, sigma I, and 0, where the sigmas are the polymatrices, which is just written here. And I is a 2x2 matrix. So these are all 4x4, right? So these are 2x2. And then I is just 1, 0, 0, 1. Now we further showed that Dirac solves the problem of negative probabilities. And when we show that the probability density rho is psi dagger psi, and the probability current density J is psi dagger alpha psi. And these are non-negative. So Dirac did manage to find a solution, which also solves the Klein-Gordon equation. So it's consistent with the relativistic Einstein's relation, E squared is equal to M squared plus P squared, which have a non-negative probability density. It's always greater than 0. And the price is that it has 4 components. And then we started to look at the spin. We didn't really have time to discuss the spin, but we did discuss the angular momentum by introducing the Dirac Hamiltonian. And looking of the commutation relation of the Dirac Hamiltonian with the orbital angular momentum L. And we showed that, in fact, they do not commute. Which means that as opposed to non-relativistic quantum mechanics, Schrödinger's equation, right, that the orbital angular momentum of the particle is not conserved. Now, at first, that sounds like a surprise, because we know that both in classical mechanics and in quantum mechanics, angular momentum is conserved. But deeper thinking says that, in fact, it doesn't have to be conserved, because the quantity that is conserved is the total angular momentum, right, J, which is the orbital angular momentum plus the internal angular momentum, which we call spin. And I'm going to show you right now that once we properly define the internal angular momentum, the spin, then indeed the total angular momentum is conserved. So in that sense, Dirac prescription is much better than the Schrödinger's one, because in Schrödinger, or the non-relativistic treatment, there is a complete separation, right? The spin and the angular momentum, they live in different Hilbert spaces. And here it is not. Here the connection between the spin and angular momentum becomes intrinsic to the problem. Now, this is as far as we managed to go to last time. So before I proceed, I'd like to stop for a second and ask you if you have any questions about anything we said so far. No, that means that everything is clear. I have to say that I am going somewhat slower than my original plan, which means that we might not cover all the topics that I was hoping to cover. I am not worried at all about that, because I don't mind if we don't cover a subject or two, but the subjects that we do cover, you will properly understand. That is much more important. Okay. But of course, I can speed up things. So if you feel that I'm going too slow, don't hesitate to tell me, and I'll be happy to speed up things, and that way we can catch up. But if I'm going too fast, also tell me, because I do want you to understand. Okay, so let's add spin. So we need to find an operator S such that the total angular momentum does commute with the Hamiltonian, right? So we want to find S, right, operator such that HD L plus S is equal to 0. So I just give you the answer, right? I'm going to consider the 4x4 matrix operator, right? Operator represented by a matrix, which is formed from the Pauli spin matrices. So I take S J, which is defined as 1/2 sigma J, sigma J operator, which is just 1/2 sigma J 0 0 sigma J. I'm just taking the Pauli matrices and I put them in a 4x4 structure. Of course, this is 0 0 here means really 0 0 0 0. I'll just write it as 1. This is a 4x4 matrix. Of course, j equal 1, 2, 3, right? X, Y, Z. Now let's look at the commutator of alpha j and sigma k. So take alpha j and sigma, sigma, take sigma k, the capital sigma. Right, in a 2 by 2 block form. Right, so alpha j, sigma k. What is that? We said that alphas 0, sigma j, 0. Sigma k is just, again, sigma k, 0, 0, sigma k. That's the commutator. So this is just the commutator here, right? Yeah, 0, sigma j, sigma k, sigma j, sigma k, 0. Right. Nothing special here. I just used the definitions. Now I'm going to use the commutation relation of the sigma matrices, which are quite straightforward to check. If we haven't, I don't remember if we did it. If not, just check it. So sigma x, what is that?
0.
0, right? Every matrix sigma commutes with itself. Sigma x and sigma y. Minus 2i sigma z. Just in case you don't remember, easily check that. So if we do that, let's take a specific example here, right? Then you have that alpha x and sigma x. That's going to be 0, right? Alpha x and sigma y. That's going to be a 0, minus 2i sigma z, and then minus 2i sigma z 0. This is just minus 2i alpha z, right? By the definition. And the same for, that's for, what did it do? Sorry, I'm confused. That's for alpha y sigma x. Well, it's pretty the same for alpha x sigma y. Okay, hopefully I didn't get too much confused with the symbols here. I think I'm okay, but check me out if I have a minus sign missing somewhere. And then the same for alpha z and sigma x. This should be 2i alpha y. Check out if I didn't miss any minus sign somewhere. And I don't need to show it because it's pretty much straightforward that beta and sigma x is equal to 0. Beta is a 4 by 4 matrix, so that needs to be a capital sigma. I still have many typos in my notes. So overall, that means that the commutator, up to a minus sign that I hope I didn't miss anywhere, that the commutator of the Dirac Hamiltonian with sigma x is H Dirac and sigma x. Just alpha dot p sigma x. So this would be just alpha x px plus alpha y py plus alpha z pz commuting sigma x. So I can simply take the P out, so it's Px, and then I have alpha x, sigma x, plus Py, alpha y, sigma x, plus Pz, alpha z, sigma x. So, so this would be a minus alpha y sigma x is just minus 2i alpha z. So it's minus 2i py alpha z plus 2i pz alpha y, which is just 2i alpha cross p x. Now this was of course for sigma x, but if I do it for sigma y and sigma z, I'm going to get exactly the same result. So I can immediately generalize that to the y and z components of sigma. And then I can use the definition of S with S is 1/2 sigma. Now you can see why I insisted on the y 1/2, because it would cancel with the 2 here. And when I do that, we have HD S is I alpha cross P. So we ended up that the operator S that we defined also does not commute with the Hamiltonian. But by now, I'm not worried about that at all, because I compare, right, the commutation relation of S with the Hamiltonian with the commutation relation of L with the Hamiltonian, right? And of course, they are exactly the opposite, because that's what I wanted. So when I merge them together, I end up that's HD and J, which is the Dirac Hamiltonian, and L is 0. Which means that it is definitely legitimate from my side to treat S as the operator that represents the intrinsic angular momentum, right? This is interpretation, but I just proved to you why this is a reasonable interpretation, right? But intrinsic angular momentum is, of course, the spin of the particle, right? So we automatically got already a better physical insight in using Dirac's notation or framework. I'm not sure what word to use. Than Schrödinger, right? Because Dirac solution shows that the total angular momentum is conserved, right? Although neither of the components, neither the orbital or the intrinsic, the spin, are conserved. So that means that we interpret S as the spin operator of, or I should say spin operator, meaning intrinsic angular momentum. Dirac particle. Well, it's really a Spinor particle. Alrighty. Now, in fact, we can do better. Now we can actually calculate what is the spin itself of the Dirac particle. So let's calculate the value of the spin. So calculate the value of the spin right, of Dirac particle. Right. So we know what is the definition of S, right? That's 1/2 sigma. So we know that the component of S obey the same commutation relations as the commutation relations between the Pauli spin matrices, right? Because S, remember, right, is just 1/2 sigma j, sigma j. Then we automatically get that Si and Sj commutation relation is I epsilon ijk. Well, it's a bad notation. Let's use j and k. Sj and Sk is I epsilon jkl SL. Right, and epsilon jkl is the Levi-Civita symbol or tensor. You're all familiar with that? Is there anybody who's not familiar with the Levi-Civita symbol? Right, it's a +1 for an even permutation of 1, 2, 3, and -1 for odd permutations, and 0 if any of these two are equal. Right? Yes, no, maybe? Yeah? Yeah, okay. But these are exactly the same commutation relation which are satisfied by the operator of the orbital angular momentum, right? Which is, this is the same as the same commutation relation, right? As satisfied by L, right? Lx, Ly, there's I, Lz, etc. And that means that I don't need to do anything because the spin is quantized exactly the same way as the orbital angular momentum, right? So in particular, right, the eigenvalues of S squared, right? So S squared, Sx squared plus Sy squared plus Sz squared, right? So the eigenvalues, what are they equal to? What are they equal to, the eigenvalues? Guys, I'm asking you.
I think you missed squared. It's Sx squared plus Sy squared plus Sz squared.
Thank you. You're right. So what are the eigenvalues of S squared? Is there anybody here who did not learn angular momentum in quantum mechanics?
So this is just 3/4, right? Because you just get I's all over.
Yeah. Yeah, but even before that, it is 3/4, of course, right? But of course it's 3/4. But S squared, right? S and MS. What is that going to be equal to?
SS plus 1.
S plus 1, right? S is some number, right? Some non-zero integer. Sorry, non-negative integer. Can be 0, of course. Right? So it's a S plus 1, S, MS. Right? So S is 0, 1, 2, non-zero integer, non-negative integer. right? Remember angular momentum, right? There is a total angular momentum and there's an angular momentum in a specific given direction, right? MS would be along the Y or Z or X or whatever direction you choose. Do you guys need to refresh your memory about angular momentum in quantum mechanics? If you do, I can help you. I mean, don't be shy. There's no point that I speak and you've got no clue what I'm talking about. It's not very hard. It's kind of basic quantum mechanics, I think. Right. So if I put direct substitution, right, S squared is 1/4 of sigma x squared plus sigma y squared plus sigma z squared. This is 3/4 because I have a 3 here of an I eventually. Right, that follows, of course, because sigma j squared is equal to I for all j. So S squared psi, just S plus 1 psi, so 3/4 I psi, or I can simply say 3/4 psi. So what is the small value, what is S then?
You mean the S times S plus 1?
Now S times S plus 1 is 3/4. So what is S?
One half.
1/2, right? So here we get so, guys, refresh your memory about about angular momentum in quantum mechanics and how it's being quantized, because I have some feeling I don't like the quietness when I ask you questions. Okay, so we ended up, I mean, look at what Dirac did, right? Just pretty amazing with all this formalism. He just took out, remember what he tried to do? He tried to find something that replaces the Klein-Gordon equation. Because he understood that there is a very deep problem with this negative probability densities. He found a solution, right? And he wrote down the Hamiltonian. He looked at the angular momentum. Angular momentum does not commute with Hamiltonian, so angular momentum is not conserved, orbital angular momentum. But when you add up another term, right, this S operator, which we identify as spin, you end up that one, the total angular momentum is conserved, and two, that you automatically get the spin of the particle to be 1/2. It's automatic. You don't need to do anything. Just put in the values in the math. Right. Very cool, isn't it? I think so. You may not agree with me. Right. Let's proceed on to explore, because we just started, as we say. The next thing I want, questions. Any questions?
Were electrons known to have spin half before that already?
Yeah, Stern-Gerlach experiment was 1924 or 25, I think. They knew about the spin by the time Dirac wrote his equation. Right? Next, the covariant form of Dirac. Any more question? So, you know, the use of the alpha, J, and beta matrices is quite useful to speak about the spin and to show what's going on there. But it's better to use a way which is covariant, which means that is the form of the equation does not change under Lorentz transformation. Covariant, its form doesn't change under Lorentz transformation. It's different than in invariant, right? Invariant means that the value, the numerical quantities do not change. Here the numerical quantities do change, but the form stays the same, right? Invariant. And the numerical values doesn't change. So how do we get the covariant form of the Dirac equation? Again, it's a very simple manipulation. So I take anything to the left first, and then I multiply by beta from the left. So I get, take all terms to the left, multiply by beta. From the left. So I can start with the Dirac equation, right? So I'll take everything to the left so that I'm getting I alpha j dj plus I dt minus beta m. Psi is equal to 0. Then I multiply by beta. And I get I beta dt plus I beta alpha j dj minus, now I have a beta squared, but beta squared is I m. Psi is equal to 0. Right? That looks cool. And I'm going to write down this in a slightly more compact form by introducing new matrices. So we define gamma 0. It's an up. It's a matrix. It's not a component of a vector or something, right? This is defined to be beta. And gamma I is defined to be beta alpha I. Right? Remember, these are matrices, alpha and beta, so the order does matter. And when I write it down like that, I have a very compact form of the Dirac's equation, which is I gamma mu d mu minus m psi is equal to 0. The covariant form. You don't have to do much. Now, okay, these gamma matrices, the gamma mu, they have several properties which they inherit from the alpha J and beta matrices. So properties of the gamma mu matrices. So let's look at a few properties. So one is multiplicity. So gamma 0 squared, what is that?
I.
I, very good. What about gamma j squared? For that we have to be slightly, to work infinitesimally harder, right? We're going to use that alpha j beta is minus beta alpha j. And then we have gamma j squared. Right? What is gamma j squared? It's beta alpha j times beta times alpha j. This is minus alpha j beta, beta alpha j. Right, so what is that?
Minus alpha j squared.
Yeah, which is equal to what? Remember? What is alpha j squared?
Minus I.
I, yeah, it's a minus I. Similarly, you have gamma mu, gamma nu is minus gamma nu, gamma mu. Right? If mu is not equal to nu. Combine this anti-commutation relation can be written in a compact form. You have the anti-commutation relation. You're familiar with that? Did I show you that? That anti-commutation relations are written in using curly brackets, right? The same way as the regular commutation relations are written with square brackets. Anti-commutation relations are written with curly brackets. It's just Q, G, mu, nu. Right. Really compact. Right, G, mu, nu, these are just the numbers, right, in the Minkowski metric. Yeah, 1 minus minus 1. So that's why we have to multiply by the identity matrix. This is one property. Second property is hermiticity. Right? What about gamma 0? Is it Hermitian?
Yes.
Yes, right. Of course, because beta is Hermitian. What about the other three matrices, gamma j? These are anti-Hermitian. Gamma j bigger, right? Is beta alpha j bigger, which is alpha j bigger, beta bigger. But we said that the matrices alpha and beta are Hermitian. So this is just alpha j beta, which is again minus beta alpha j, using the anti-commutation relations, which is just minus gamma j. So gamma 0, then there is gamma 0, and gamma j, there is minus gamma j. Nice and easy. Now, in principle, that's everything we need to know about these gamma matrices. Because what we really care about, this is something which is, it takes time to understand. At least for me, it took time to understand when I was a student. This is everything we need to know about the gamma matrices, because we can take these matrices and represent them in all sorts of ways that we want to. But in reality, in practice, what's going to happen is that when I'm going to ask you to write these matrices, you're going to write them down in using a certain representation. So let's just put the representation, which is common. That's called the Dirac Pauli representation. So right, you can use more than a single representation, but in reality, we do use the Dirac Pauli representation for most practical purposes because it's nice and easy. And although it's only a specific one, right? So for that, gamma 0 is just beta, it's just I 0, 0 minus I. And gamma j is just beta multiplied by alpha j. So this is just going to be 0 sigma j minus sigma j 0. And if you want to expand that, just to see how it really looks like, so gamma 0, right, it's really 4 by 4 matrices. 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. That's how it looks like. Right? And gamma 1 is going to be 0, 0, 0, 1, 0, 0, 1, 0, 0, minus 1, 0, 0, minus 1, 0, 0, 0. If I'm only writing it, that's finished. Right? Gamma 2 would be 0, 0, 0, minus I, 0, 0, I, 0, 0, I, 0, 0, minus I, 0, 0, 0. And gamma 3 is the only one which is a little bit of interest. Right? The sigma 3, it's a 1, 1, minus 1. So it's a 0, 0, 1, 0, 0, 0, 0, minus 1. And then a minus 1, 0, 0, 0, 0, 1, 0, 0. So that's the most commonly used representation of the gamma 0 and gamma j matrices. Now, as a comment, right, we're seeing in the Dirac equation there is this gamma mu d mu, right? This is not a Lorentz scalar because gamma mu is not a vector. So gamma mu is not a vector. So gamma mu d mu is not the Lorentz scalar. Right. Rather, remember, we spoke about covariance. These are simply 4 matrices, which numbers, and these numbers are not affected by any Lorentz transformation. Right, so the matrices stay the same under any Lorentz transformation, any frame that you choose. All right. Now we do want to show the full covariance of Dirac. Any questions about that, by the way, before I proceed? No, I do want to show any questions. No, nothing.
So gamma mu in a way is a vector of matrices, right?
Yeah, it's a compact notation of writing it. Yes, but yeah.
Right, but I don't. It's not obvious to me why this is not a Lorentz scalar. So why is it straightforward? Why is it straightforward? I mean, I believe the claim, but just because gamma mu is kind of a vector of matrices, what? I mean, gamma mu d mu is not a number, but that doesn't mean it's not a Lorentz scalar, does it?
Well, it's a number. The gamma mu by himself, yes, but they're multiplied by d mu.
So you get a matrix of derivatives, right?
D mu is a vector. It's a four vector, right?
Right, and gamma mu is a kind of a 4 vector of matrices. So this multiplication, if I carry it out, I'll get a 4x4 matrix where each element is either dx or dt or something like that, right?
Yeah, it will be simply multiplied by a different matrix. You know what? I'm going to do it right now. So maybe wait with your question another 10 minutes. Because that's what I want to do now. I wanted to show you directly that Dirac equation is covariant. Right? So in the sense that I can take a Lorentz transformation for the spinor, for psi, right? Such that the equation does not change when I'm looking on the equation between two different frames. I guess that's what you're aiming on. So let's look at that. So let's see the next thing I want to do is to give you a direct proof of the covariance of Dirac equation.
That means the Hamiltonian itself is not a Lorentz scalar, right?
That means that the Hamiltonian, yes, that's true. Okay, I want to show you directly the covariance of form of Dirac equation. Right? How are we going to do that? Let's take a frame O, which has coordinates x, mu. So consider frame O with coordinates x, mu. Right? In this frame, the frame O, right, psi satisfies the Dirac equation. Psi of x satisfies Dirac equation. Right, so I gamma mu d mu minus m psi of x is equal to 0. Okay. Now, if this equation is to be a Lorentz covariant, it means that I'm now looking at this from the point of view of a second observer. So now we have a second observer. It's a frame O prime, right? Which has coordinates x mu prime, And the second observer would argue that the wave function as he sees it, right? So psi prime x prime must satisfy a similar equation, equation of the similar form. Argues, so coordinates x mu prime, argues psi prime x prime satisfies the same equation, which is I gamma mu. Now it's a new coordinate, so it's d mu prime. Right, gamma mu is not changed because it's just numbers, right? Minus m psi prime of x prime is equal to 0. Now, that means that if the Dirac equation is to be covariant, right, then we must find some matrix, a 4x4 matrix, right, that transforms the spinor between the two frames. So in order for the equation to be covariant, we must find a 4x4 matrix S, right, that transforms the matrix between the wave function between the two frames, such that psi prime x prime is S psi of x. Now we have to be a bit careful in how we do it, but let's see if such a matrix S exists. Well, it is, because otherwise I wouldn't tell you that it's covariant. Now, we have the four derivative. M is a constant, gamma mu are constant, so we don't care about those, but we have the four derivative. The four derivative, this is a covariant vector, right? D mu, the covariant vector. So because it's a covariant vector, it transforms under the inverse of a Lorentz transformation, right? So D mu prime is lambda nu mu D mu, D prime mu. Becoming the way, or no, it's fine to do it like that. Right, remember that this is the symbol of the inverse. So if I write it down, what did I do? Okay, they required the form of the Dirac. Okay, so I'm confused myself with the notation. Okay, let's do it the way I wrote it here, though I'm not even sure that I wrote it in the right way. That's what happened when you work over hours. So I put the prime on the derivative, which I'm not so sure that I'm allowed to do, and then there will not be a prime here. I have to check my notations. Yeah, well, I guess I can do it. You know what? It doesn't matter. Sorry, I'm just confusing you now. Let's write it down like that. So if I put the prime on the mu, which is to be more, that's the right thing to do because I'll be more consistent. Then I'll have to write down, this is prime, this is prime, this is prime, this is prime. So then it's okay. Then I write down this equation, the Dirac equation in the second observer's frame. It will be written as I. Okay, there. Rather than mu prime, I can write this nu prime. So it will be I gamma nu prime, lambda nu prime mu d mu minus m, and then S psi of x is equal to 0. Okay, now everything is in order. Now the S matrix, it's just a constant matrix, right? So I can take it away from the derivative. Right? So d mu of S psi is just S d mu psi. Right? S is not dependent on the coordinates. So I have I. Now remember that the new prime here is a dummy, so I can remove the prime because it's just a dummy index. So I have I gamma nu lambda nu mu S d mu psi of x minus m S psi of x is equal to 0. So what did I get? Okay, so I got that, a covariant form of the Dirac equation. Sorry. So now I can take that equation and compare that to the original Dirac equation in the original frame O, right? To this equation here, right? I gamma mu d mu minus m. And I gamma mu lambda mu mu s d mu. So I can take this original Dirac equation and multiply it by s from the left. So original Dirac equation, and I take it and multiply by s from the left. And we have I s gamma mu d mu minus ms psi x equal to 0. Which means that I can obtain a Lorentz covariance of the Dirac equation if I can find a matrix S, right? Which, if these two terms are the same, right? If the term here is equal to the term here. In other words, if I can show that if S gamma mu is gamma nu lambda nu mu s, then we get a covariant form. Dirac equation. So this is the condition that the matrix S needs to fulfill in order for the Dirac equation to be covariant, right? Now, okay, there is such a matrix. I'm not going to do the general term because it's kind of annoying, but let's look at the specific example. Right. Let's say that the frame O prime travels in the z direction, its velocity some plus v. Assume O prime travels in this velocity plus v in the z direction. No, with respect to O. Then the inverse Lorentz transformation, lambda nu mu, is just gamma 0 0 gamma beta. It's a plus here because if O prime travels in the plus z, then from the inverse transformation will be with a minus. So that's why the plus here. 0 1 0 0 0 0 1 0 plus gamma beta 0 0 gamma. And then I just take that relation here and write it explicitly. So we have S gamma 0 is just gamma 0s plus gamma beta gamma 3s. And S gamma 1 is just gamma 1s. S gamma 2 is just gamma 2s. S gamma 3, again, it's just gamma beta gamma 0 s plus gamma 3s. The notation is slightly misleading, right? Because gamma is the Lorentz factor and gamma with an upper index is the gamma matrices. Or the gamma matrices. So, it's now we have to plug in the values of the gamma matrices inside, and you would get a solution. You can trust me on that. The solution would be S would be A I minus B gamma 0 gamma 3, and A is just square root of 1/2 gamma plus 1, and B is square root of 1/2 gamma minus 1. So if you plug these solutions, then you find that both this solution satisfies all the conditions here. And no less important, S approaches the identity matrix, right? When gamma goes to 1, right? When gamma goes to 1, A approaches 1, B approaches 0, so S approaches the identity. So we just found the matrix S, which describes the transformation properties of the Dirac Spinor for a Lorentz transformation in the plus Z direction. Using this matrix, right, the mathematical form of the Dirac equation is preserved, which means that it is a Lorentz covariant. Now, this is one example for the Z direction, but it's quite obvious that since the choice of the Z direction was arbitrary, you can choose it in any other direction. It's just going to get the nasty matrices if you choose to do a general solution. But conceptually, there's nothing different or alarming. Questions?
Can we then find a formulation which is manifestly covariant with proper vectors?
Not sure what do you mean by vectors. You mean the Dirac equation? The Dirac equation is written with the gamma matrices. You cannot avoid it.
Yeah, but can I have a vector of matrices, a vector that transforms as a Lorentz vector, not with this artificial S matrix?
Not that I know of. From the form I know, because the Dirac equation, you always have this combination of gamma mu as the matrices multiplied by d mu, which is a vector. And these matrices are constant. You can find other representations, but I don't think you can, in which they would simply get a different form, but they would still get constant values. I'm not aware of any other way of putting Dirac, writing down Dirac equation in another form. This is the standard way of writing Dirac equation, and I just showed you that it is covariant.
So M is a Lorentz scalar.
Yeah.
And d mu is a Lorentz vector.
Right.
So we have an equation. Okay, it's an operator equation, but it's composed of Lorentz vectors and Lorentz scalars plus this gamma mu. And 0 is a Lorentz scalar as well. On the right-hand side.
Yeah.
So it should be possible to have the gamma mu written in some combination to form a Lorentz vector, because you should have a covariant equation.
We will be speaking, I hope, well, I have to choose which to cut off. There are these things which called Dirac bilinears. So we'll reserve this question for, I think, 2 or 3 lectures, then we'll speak about them. The Dirac bilinears. Maybe this will help you get a more mathematical insight, more insight on the inner mathematical structure of these scalars, vectors. There will be pseudo vectors and pseudo and tensors, which I'll include. I was kind of thinking I may skip that part because it's I'm not sure if it's totally needed, and we're somewhat short in time. But if you're interested in the mathematical structure, I'll simply put it in, and we'll discuss it. To answer your question directly, I do not know of any form of writing down Dirac equation in using only vectors. But I will check out because I may not know all of it. Maybe there are some ways which I'm not aware of or that I forgot of or something like that.
Okay.
Okay. Are there more questions? Okay. Now I want to discuss the covariant current and the adjoint spinor. How much time do we have, by the way? Oh, it's okay. Covariant current. And adjoint spinor. Okay, so we've already defined the probability density and the probability current density, right? So rho is just psi dagger psi, and J is just psi dagger alpha psi. Now I can use the relations gamma 0. Use gamma 0 squared is just I. So I can plug it in here. And gamma 0 gamma I is just beta times beta alpha I. This is just alpha I. So I can replace the alpha I here with gamma 0 gamma I. And I can take these two expressions that I have here and write them in a more compact form, which will be J mu. Now this is going to be a 4-vector. Rho and J is just psi dagger, gamma 0, gamma mu, psi. Right. Now, it can be verified that J mu is a proper 4-vector. I'm not going to give you the full proof, but it appears in the appendix in the book by Mark Thompson. Mark Thompson, I think, yeah. In appendix B, you'll find the solution, the full proof there. Now, if we want to, we can further simplify this expression by introducing the adjoint spinor. So adjoint spinor. Right, which is defined, psi bar is defined by psi dagger gamma 0. And then I can write down, using this, I can write down J mu as psi bar gamma mu psi. And of course, again, we had the continuity equation, ET rho plus nabla J is equal to 0. Right. This, of course, is written in a compact form. B mu J mu is equal to 0. I think we wrote it already. Just for completeness, right? If we use the Dirac Pauli representation of the gamma matrices, then the adjoint spinor of psi in the Dirac Pauli representation, right? We had psi was psi 1, psi 2, psi 3, psi 4. And then psi adjoint is just psi 1 star, psi 2 star, minus psi 3 star, minus psi 4 star. Using the definition, the representation of the gamma matrices in the Dirac Pauli representation. All right. More questions? Any questions? There are a few students here that I never heard them speaking. Guys, it's a small class. And I'm here for you. I actually mean it. Any questions or comments or requests or anything you want? No? Okay, the next thing I'm going to do, we're going to solve the Dirac equation. So now let's look at solutions to the Dirac equation. Okay, so the first thing, of course, we're going to follow the same thing that we did for the quantized Maxwell equation, right? So we're looking for free particle plane wave solutions of the form. Research, we look for free particle plane wave solutions. Right. Be psi of x and t, and just u, e, and p, and then ei, ex minus et, which is u, e, and p, e minus I, p mu x. We did it already, right? I'm not saying anything which is new here. Guys, is that clear to everybody? I don't want to go 1-1 and ask you if it's clear. Is it clear to you guys? Say yes or no.
Yes.
I had 1 yes out of 7.
Yes.
Yes, I had 2 yeses.
Yes.
Yes, yes, yes.
תמשיך.
Okay. So now also the term, the U is also called the Dirac Spinor in this presentation. So when I say Dirac Spinor, when you look at the plane wave solution, sometimes it's referred to the psi and sometimes it's referred to U. Of course, this psi, as a psi, satisfies the Dirac equation. Now, since the dependent on position and time appears only in the exponent, right, in the plane wave solution, right? The U, right, this is just a function of the energy and the momentum, right? So the entire dependence of the time and x is in the exponent, right? So when I take the derivative, right, in the Dirac equation, then d0 psi, we get minus I e psi, and dj psi is just I dj psi, right? So d1 is d over dx, d2 is d over dy, right? Now, if we plug this into the Dirac equation, right? What do we have? We have gamma 0 E minus gamma J Pj minus M psi is equal to 0. Now, I don't care about the spatial part because it's in the exponent, so I can simply look at the equation for U, and we get that gamma mu P mu minus M U is equal to 0. Right? So now we ended up with an algebraic equation. This is an algebraic equation that describes the free particle spinor in U, and there are no derivatives here. Right? It's algebraic equation describing the free particle spinor. right? No derivatives. So let's start by something simple. Let's consider first particle at rest. Right, so for particle at rest, what do we know about particle at rest?
Momentum is 0.
Yeah.
Zero.
E is equal to 0. So psi is u of E and 0, E minus I ET, right? Using that in the algebraic Dirac equation, we end up with the E gamma 0 U equal to mu. Now remember, I wrote down specifically what is gamma 0, right? So this is can express that as an eigenvalue equation for the components of the spinor. So we have E, right? Gamma 0 is just 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Times phi 1, phi 2, phi 3, phi 4. Just m, phi 1, phi 2, phi 3, phi 4. Right? So gamma 0, I wrote it down somewhere. Here it is. This is gamma 0. And phi are the 4 components of the spinor U. Right? So gamma 0 is diagonal. There's no problem. So we have 4 orthogonal solutions. Yeah. Which are immediate, right? So just U1, 1, 0, 0, 0, U2, 0, 1, 0, 0, U3, 0, 0, 1, 0, and U4 is just 1, 0, 0, 0, and 1. Okay, pretty cool. 4 orthogonal solutions. Up to normalization, which I elegantly skipped. Right. So if I look at the first 2, what are the eigenstates? Oh, sorry, what are the eigenvalues?
One.
What is the energy of these states? What is the energy of these states?
The mass.
M, right? So we have the energy, positive energy eigenvalue. What about these 2?
Minus M.
Minus.
Right? These have 2 negative energy eigenvalues. Now remember, right? We had this Feynman-Stuckelberg interpretation, right? So minus M times T is just M times minus T, which enables us to interpret these negative energy states, right, as really positive energy states of particles that move backward in time. It's an interpretation. But what do we get? We get basically anti-fermions. Remember, I promised you, right? Dirac ended up with search for solutions for, Einstein's equation, essentially, but with non-negative probability density, ended up finding 4 solutions, right? So we see 2 solutions have a positive energy, 2 solutions have a negative energy. What about the spin of the solutions, right? So 4 states are also eigenstates of the spin operator, SZ, right, which you already defined. So SZ spin let's say of U1. Right? Remember, SC is 1/2 sigma Z 0, 0, sigma Z, acting on U1. So it's 1/2 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. And U1 is just 1, 0, 0, 0. So just 1/2 U1. So U1, right, represents a what? Represents a spin up plus 1/2, right? Positive energy solution. Of the Dirac equation. What about U2? What does it represent?
Spin down of the energy solution.
Sorry, again? I couldn't hear you.
Spin down.
Spin down, right? It represents a spin down. And again, with a positive energy. Right? What about U3?
Spin up of the antiparticle.
Spin up of a negative energy, right? It could be a spin up of a negative energy. Right? Because SZ U3, you can clearly see from here from the matrices, right, will just be 1/2 U3. And SZ U4 would be minus 1/2 U4. So U4 would be a spin down negative energy. So the Dirac equation, as promised, give us, right, 4 solutions. Each one has its own physical interpretation. Spin up and spin down, positive versus negative energy. Okay, this was easy. Now let's generalize that. Any questions before I generalize? Question? Any? None. Okay, so let's generalize that to any free particle solution, right? This is for particles at rest. What if the particles are not at rest? So general free particle solution. I repeat again, is there any questions? At this point, I'm pretty sure that you have not seen that before, unless you already took a course in quantum field theory, which you might then. Not even sure that. Is there anybody who has seen these things before? No. So I want to make sure that I'm not rushing too fast. It's not that hard, but it takes time to, if you see the picture, it's quite easy. If you get confused because you're not that, you don't feel that comfortable with operators and concepts in quantum mechanics, then what I'm saying you can get lost here very quickly, and I don't want that to happen. Make sure it's your responsibility to make sure that you're not losing me. If you don't understand something, drop me an email if you don't want to ask here. I'll guide you where to look for, and I'll put my lecture notes online after I finish cleaning up all the typos that I put in. Okay, so now let's look at the general free particle solution. Okay, so we have the full equation, gamma mu p mu minus m u is equal to 0. So we're going to write down the Dirac equation. using the Dirac Pauli representation. Representation of the gamma matrices. So gamma 0 is just I 0, 0 minus I. I'm doing the 2 by 2 block form, right? Times E minus 0 sigma dot P. Sigma dot P is a minus 0. And minus I 0, 0 I m. U is equal to 0. Now the sigma dot P, that's the one that is going to be give us the most algebraic problems. That's simply written as PZ Px minus I Py Px plus I Py and then a minus Pz. Right now this is a block, right? It's a 2 by 2 block. Now I can write down the spinor in terms of two component column vectors, UA and UB. Right? So I'm going to write down U as UA, UB, right? But UA and UB are two components each, right? Don't get confused here by the shortened of notation. And so I have this equation, which I merge it together into one big form. That's going to be E minus M I minus sigma dot P, sigma dot P, then minus E plus M I, UA, UB is equal to 0. Okay, that's quite straightforward. And that gives us a coupled, two coupled equations. So we have UA, just sigma dot P over E minus M UB, and UB is just sigma dot P divided by E. Vector, stupid. Sigma dot P divided by E plus M UA. Okay, so we have total of 4 solutions to the Dirac equation, right, as we just saw previously. Now we need to obtain them. And in order to obtain them, we can simply choose the 2 simplest orthogonal solutions for UA and then plug in for UB and be happy. So we choose like UA is 1, 0 and UA is 0, 1. And just plug it in and calculate right down here. And just plug it into this equation. And
should be UB.
Sorry?
UB at the right side.
No, the right side is UA. You have 2 solutions. You have 2 orthogonal solutions for UA, right? It's a 2 component. UA. 2 component each. Right? Don't get confused by the short of notation. This is a 4 by 4. This is a 4 by 4 matrix, just written in a 2 by 2 block form. And U is a 4 spinor, right? 4 component spinor. Okay, thanks for pointing it out. That's quite important. This is a 4 spinor, which I just write it, each one of those UA and UB, right? These are 2 by 2. So overall, we have a 2 by 1, sorry. So overall, we have a 4-component spinor. Okay, so I just choose 2 orthogonal solutions for UA. And then I plug them in here using sigma.p. And the results up to normalization that we're going to have, which I'm elegantly skipping. I mean, the normalization is not that trivial, by the way. That's why I'm elegantly skipping it. It's a relativistic normalization. That's why I try to hide it under the carpet. It's a U1 plug in and get U1 of E and P is 1, 0. That's the UA. And the UB will get a PZ divided by E plus M and a PX plus IPY divided again by E plus M. So that's the first solution. The second solution would be U2 of E and P is just 0, 1. And then it will be Px minus IPY divided by E plus M and minus Pz divided by E plus M. So these are the 2 solutions, orthogonal for UA. Now I can choose, again, 2 solutions for UB. Again, the same trick. UB is 1, 0, and UB is 0, 1. And again, I'm going to use that in here to calculate, or in here to calculate what is UA. And the corresponding is going to be U3, which will be Pz divided by E minus M, and then Px plus IPY divided by E minus M, and then a 1, 0, and a U4, which is Px minus IPY divided by E minus M, and then a minus Pz divided by E minus M, and then a 0, 1. So we got 4 independent solutions. Each one is a solution of the Dirac equation, right? So that should be clear. Each one of these solutions is a solution of the Dirac equation. I put it into the Dirac equation. Let's see something if I do like that. Aha, it does do it. Very nice. So if I plug it in, each one is a solution of the Dirac equation. Each one of those fulfills the Einstein's relation, right? Each is a solution to Dirac equation, and each fulfills E squared is equal to P squared plus M squared, right? Of course, in the limit where P goes to 0, we retrieve back the solutions we had, the simple solutions we had previously for particles at rest, right? So again, that means that U1 and U2 can be identified as the positive energy spinors with the positive energy, and the U3 are in U4 are the negative energy particles. So in the limit P goes to 0, we retrieve the solutions for particles at rest. Okay, the next step is to go and interpret these negative energy solutions as the antiparticles. But I
Asaf, can I ask a question to the solution?
Yes, please.
The fact that when P goes to 0, we go back to this simple, the 1, 0, 0, 0, and so on solutions. does this mean that at non-zero momentum, the particle and antiparticle mix in some way? Because you're now, because U1 with non-zero P is kind of a superposition of U1, U3, and U4 with P equals 0.
No, these are orthogonal solutions.
No, if I take U1 with P with non-zero momentum, it's a superposition of the 3 zero momentum solutions, U1 and U3 and U4.
I'm not sure what it means, if it has any meaning, because you're solving.
That's my question. That's my question. Does this have a meaning, or is it just?
No, I don't see any physical meaning, because you're solving different equation, right? This is a solution to Dirac. This is a general solution to Dirac equation with a non-zero momentum. And the U1 and U4 are solutions to Dirac equation with 0 momentum. So it's not the same equation. So I'm not sure that I understand what would be.
Because P is a conserved quantity, it cannot tune. It's not an external parameter I can tune in some way, right?
P is the momentum. That's what you're saying for the particle in a given frame.
Right.
So basically,
Okay.
you can look at this, you're trying to mix solutions in different frames, which is of course illegal.
Right. Okay, I see what you're saying. Okay, thanks.
Okay. Any further questions? No? Okay, we're over time a little bit. Guys, I do want to encourage you. We got into some technicalities. I mean, the beginning I tried to take it slow and take it, not much technical details, but now we are doing technicalities. Again, we can make it worse. If you do it in quantum field theory, it will be worse. But I'm not doing the full quantum field theory, because I'm doing it in the level which is, to my opinion, should be accessible to people who just started to, don't have that much of an experience with quantum mechanics. But you still do need to know some basics of quantum mechanics to be able to follow. So if you don't feel comfortable with anything I'm saying, make sure that you tell me that, because I cannot read your minds. I can only listen to what you say, and some people ask questions, so I'm pretty confident in what they understand, but other people do not ask. So it's very difficult for me to know what you understand and what not. Okay. So I think that's the end of today's lecture, and then we shall meet again on Thursday, I believe. Happy
I have a general
Hanukkah.
question.
Yes.
So more, say, conceptual one.
Yeah.
We use representations of the alpha matrices and essentially the gamma matrices.
Yeah.
We represent them as matrices. Is this the only representation of them as 4x4 matrices? Only at least up to conjugation?
No, I don't think so. I think in the 4x4 you do have the freedom to choose more than one representation.
So what I'm asking is there a representation which is significantly different? Say,
I think there is, but I don't remember it by heart, because I haven't looked at that recently. I think there is, but I have to check it out to give you.
Is there any physical meaning to choosing this other representation?
I have to check. I cannot answer to you. I just don't remember the answer right now. I think there is. Yes, the Weyl representation. I just mentioned it briefly. That's good for zero mass particles. This is for massive particles. I think. Look, I remember that there is something, but I don't remember the details. I need to refresh my memory before I can answer that.
Sure.
Remember what I mentioned at the beginning of, or sometimes during the lecture. The important part really, conceptually, is not the representation, is the algebraic relations that the matrices fulfill. Essentially, every choice of matrices that will fulfill these anti-commutation relations, essentially that leads us to the Grossman algebra, which I don't know if you've seen. this is good for our purposes. So now it's a question of finding a representation which will fulfill these anti-commutation relations. I'm pretty sure that in 4x4 you have more than a single one. But honestly, I don't remember the details, so I don't just want to say something which I don't remember.
Okay, thank you.
Okay. More? If not, then have a happy Hanukkah. And I see you all on Thursday, I believe.
Thank you.
Thank you, and
Thank you very much.
have a great rest of the day. Stay safe from the storm that is supposedly coming.
Bye-bye.
Bye-bye.
Bye-bye.